I am going to give you two sets of numbers. I want you to tell me which one is bigger. Set 1, the natural numbers. 1, 2, 3, 4, 5, 6, 7, on and on, forever. An infinite list that never ends. Set 2, the real numbers between 0 and 1. Every decimal, 0.1, 0.5, 0.333 repeating, pi divided by 4, the square root of 2 divided by 2, every number you can write as an infinite decimal between 0 and 1. Both sets are infinite. Both go on forever. Your instinct says they are the same size. Infinity is infinity, right? Wrong. One of these infinities is strictly, provably, inconceivably larger than the other. And I can prove it in under 15 minutes using an argument so simple that a bright 12-year-old could follow it, yet so profound that it shattered the foundations of mathematics when it was published in 1891. This is Cantor's diagonal argument, and once you understand it, you will never think about infinity the same way again. Let me start with a question that sounds absurd. How do you measure the size of an infinite set? You cannot count to infinity. You cannot finish the list. So how do you compare two things that both have no end? George Cantor's insight was this: you do not need to count, you just need to match. If you compare every element of set A with exactly one element of set B, with nothing left over on either side, then the two sets are the same size. This is called a bijection, a perfect one-to-one correspondence. Think of it like a dance. If every person in the room has exactly one partner and no one is left standing alone, then there are the same number of men and women. You do not need to count heads. You just need to see that the pairing is perfect. So let us try this with the natural numbers and some other infinite sets. Can we pair the natural numbers with the even numbers? It seems like we cannot. The even numbers are a subset. You are throwing away all the odd numbers. There should be fewer evens than naturals. But watch. Pair 1 with 2, pair 2 with 4, pair 3 with 6, pair 4 with 8. Every natural number n maps to the even number 2n. Every even number is hit. Nothing is left over. The pairing is perfect. The set of natural numbers and the set of even numbers have the same size. This is already strange. A proper subset, a set that is missing half its elements, is the same size as the whole. This is a defining property of infinite sets. It is, in fact, how mathematicians define what it means to be infinite. Now try the integers. All positive and negative whole numbers plus 0. Surely there are more integers than natural numbers. You have all the naturals plus all the negatives plus 0. That is 3 times as many, roughly. But we can pair them. Map 1 to 0, map 2 to 1, map 3 to -1, map 4 to 2, map 5 to -2, zigzag between positive and negative. Every integer gets a natural number partner. The pairing is perfect, same size. What about the rational numbers? Every fraction, 1/2, 2/3, 7/5, -11/3. The rationals are dense. Between any two rationals, there are infinitely many more. They seem to fill up the number line with no gaps. But Cantor showed they are countable too. Arrange all positive fractions in a grid. Row 1 is 1/1, 1/2, 1/3, 1/4. Row 2 is 2/1, 2/2, 2/3. Row 3 is 3/1, 3/2, 3/3. Now zigzag diagonally through the grid, skipping duplicates. You hit every positive fraction exactly once. The rationals are countable, same size as the naturals. So everything is countable. Evens, integers, rationals. No matter how cleverly you build an infinite set, it always seems to have the same size as the natural numbers. Cantor asked the obvious next question. What about the real numbers between 0 and 1? And here is where everything breaks. Suppose, for the sake of contradiction, that the real numbers between 0 and 1 are countable. That means we can list them. all of them. In a numbered sequence like this, number 1 on the list is some decimal, say 0.517092, and so on forever. Number 2 is another decimal, 0.834165, and so on. Number 3, 0.297508, and so on forever. Every real number between 0 and 1 appears somewhere on this list. That is the assumption. We are assuming a complete list exists. Now I am going to construct a number that is not on the list. Look at the first digit of the first number. It is 5. I choose a different digit, say 6. Look at the second digit of the second number. It is 3. I choose a different digit, say 4. Look at the third digit of the third number. It is 7. I choose 8. The fourth digit of the fourth number. The fifth digit of the fifth number. The sixth digit of the sixth number. At each step, I look at the diagonal, the nth digit of the nth number, and I choose something different. This gives me a new decimal, 0.648, and so on. A specific real number between 0 and 1. Is this number on the list? It cannot be number 1 because it differs from number 1 in the first digit. It cannot be number 2 because it differs from number 2 in the second digit. It cannot be number 3 because it differs in the third digit. It cannot be number n for any n because it differs from number n in the nth digit. This number is not on the list, but we assumed the list was complete. We assumed every real number between 0 and 1 was included, and yet we just constructed one that is missing. Contradiction. The assumption is false. The real numbers between 0 and 1 cannot be listed. They are uncountable. There is no bijection between the naturals and the reals. The reals are a strictly larger infinity. Let that sink in. There are more real numbers between 0 and 1 than there are natural numbers in all of existence. More reals in that tiny interval than there are integers, positive or negative, stretching in both directions forever. More reals between 0 and 1 than there are fractions in the entire rational number line. The infinity of the reals is bigger. Cantor called the size of the natural numbers Aleph null, the first infinite cardinal number, and he showed that the reals have a strictly larger cardinality, which he called the cardinality of the continuum, denoted c, and c equals 2 to the power of Aleph null. Why 2 to the Aleph null? Because every real number between 0 and 1 can be represented as an infinite sequence of binary digits. 0 or 1, repeated forever. The set of all such sequences is the power set of the natural numbers, the set of all subsets of the naturals, and the power set of any set is strictly larger than the set itself. This is Cantor's theorem. For any set S, the power set of S has strictly larger cardinality than S. The proof is almost identical to the diagonal argument. Assume a bijection between S and its power set. Construct the set of all elements that are not in their paired subset. This set cannot be paired with any element. Contradiction, and this means the tower never stops. Take the power set of the reals, that is a larger infinity. Take its power set, larger still, Aleph null, then c, then 2 to the c, then 2 to the 2 to the c, an infinite hierarchy of infinities, each strictly larger than the last. There is no largest infinity. The concept of size itself has no ceiling. When Cantor published these results, the reaction was violent. Leopold Kronecker called him a corrupter of youth and a charlatan. Henri Poincaré called his ideas a grave mathematical disease from which future generations would one day recover. David Hilbert, one of the few who defended him, later declared that no one would ever expel Cantor from the paradise he had created. The mathematical establishment was not ready for the idea that infinity comes in sizes. Cantor suffered repeated mental breakdowns and spent the final years of his life in and out of psychiatric hospitals. He died in a sanatorium in Halle in 1918. But he was right. Every branch of modern mathematics is built on his foundations. Set theory, topology, measure theory, functional analysis. The uncountability of the reals is not an exotic curiosity. It is why calculus works. The completeness of the real number line, the property that makes limits and continuity possible, depends on the reals being uncountable. If the reals were countable, you could assign a positive measure to each one and derive contradictions with basic integration. There is one more question that Cantor asked but could never answer. Is there an infinity between Aleph, null, and C? Is there a set larger than the naturals but smaller than the reals? Cantor believed the answer was no. This belief is called the continuum hypothesis. In 1938, Gödel showed it is consistent with standard set theory. In 1963, Cohen showed its negation is also consistent. The continuum hypothesis is independent. It can be neither proved nor disproved from the standard axioms of mathematics. It is a question that mathematics, as currently formulated, cannot answer. So let me leave you with this. You started with two infinite sets, the natural numbers and the reals between 0 and 1. Both infinite, both endless, and yet one is so much larger than the other that no possible pairing can bridge the gap. Not a clever pairing, not a complicated pairing, no pairing at all. The proof is 6 lines long. Look at the diagonal, choose different digits, the new number is missing, done. Infinity is not one thing. It is a staircase that goes up forever. And the first step, the gap between countable and uncountable, was discovered by a man the world tried to destroy for telling the truth. That is Cantor's diagonal argument, and it fits on a napkin.